Hi to everyone, my name is Álvaro Porras. I'm a member of Oasis Research Group at the University of Malaga. I'm going to present this work that is titled An Efficient, Robust Approach to the Day-Ahead Operation of an Aggregator of Electric Vehicles. It's a joint work with Ricardo Fernández Blanco, Juan Miguel Morales, and Salvador Pineda. Okay, currently there is a growing penetration of electric vehicles in the electricity system. As a consequence, new agents appear as the aggregator of electric vehicles. This aggregator takes decisions about when to buy or sell energy in the electricity market, to charge or discharge the EVs. These decisions are conditioned by the inherent uncertainty in driving habits, as the arrival times, leaving times, or distance traveled. In this work, emphasis is placed on the uncertainty in the EV availability. And this uncertainty is dealt using hierarchical optimization. First, I'm going to present a standard method to model the operation of an aggregator. The first one, the deterministic formulation, and this method doesn't consider the uncertainty in the EV driving patterns. The solutions are optimal for expected value, but an advantage is that this method is computationally tractable. It's like a visionary who can predict the future, but in real life, future is unknown. The stochastic formulation considers uncertainty using scenarios, but has two main drawbacks. It's optimal, the solutions are optimal for on average, and to obtain great results, you need a large number of scenarios. So that's the reason we propose a novel method, the hierarchical formulation. This method considers uncertainty using a few intuitive parameters that is very practical in our daily life. The solutions are robust against adverse situations, and if the number of variables increase, the method continues being faster than the stochastic counterpart. It is like a superhero, okay? Well, I'm going to present the deterministic formulation as a simple way to model the operation of an aggregator. The electricity price are expected values for all the method and in this work, okay? In the objective functions, we find three terms. The first one is the operational cost, the second one, the battery degradation cost, and finally, a penalty cost due to the violation of this constraint, okay? This is the power balance of the aggregator, the charging variable of the EVs, and the discharging variable, the feeder capacity, the energy stored into the battery, the energy which enters into the battery, the energy extracted from the battery, the energy consumption of the EV, the maximum rate of power charging and discharging, the bounds of the energy stored into the battery of the EVs, the boundary condition of this variable, and this is the battery degradation cost. This is a linear model, and the non-negative character of the decision variables. This set of constraints is identical for all the methods, so it can be represented by the letter phi in terms of expected value. In this case, expected values of availability and energy consumption. Now I'm going to explain how to obtain an availability profile and expected value of availability profile. Okay. Well, this is an availability profile, and when the availability is 1, the EV is available to charge or discharge, and when the availability is 0, the EV is unavailable. We have here for historical profile, and to obtain the expected value of availability profile in the deterministic formulation, the expected value is the average of all the profiles, okay? For example, in this time period, the availability is 0, 0, 1, 1. So the expected value for this time period is, is 0.5, which means that the EVs can only charge the 50% of the maximum rate of power charging. If you do that for all the time period, you obtain an expected value of availability profile. Right. Each profile in the stochastic formulation is an scenario, so it's a simple way to model. But as I say, in the deterministic formulation, the uncertainty is not considered, the solutions are optimal for respective values. In the stochastic formulation, sorry, the solutions are optimal on average and you need a large number of scenarios. So that's the reason we propose a novel method, the hierarchical formulation. In this novel method, the uncertainty in the EV availability is characterized by a parameter set. Now, the availability is a variable and depends on an uncertainty set. In this constraint, we impose that the EV must be available at least k time periods. We impose here the minimum value and maximum value of alpha, the availability, and the binary character. Now I'm going to explain how to obtain each parameter. The k parameter is the minimum time periods that the EV must be available. If we observe historical data, we can observe that in this profile, the EV is available 18 time periods, in this one 13, 14, and 11. So the key parameters is the average of all the available time periods, and we take the floor integer. So the EV, for this case, the EV must be available at least 12 time periods. Alpha minimum is a vector of zeros for each profile, and alpha maximum a vector of 1 for each profile. But if we observe the historical data, in these time periods, here, the EV is always available. So we can assume that the alpha minimum is 1 because it's logical because the driver is sleeping, for example. And in this time period, the EV is always unavailable. So we can assume that the EV is 0, the maximum value of the availability is 0 because, for example, the driver is working. Well, we obtain those parameters, and this is the structure of the hierarchical formulation. Well, this figure conceptually represents the interaction among the electricity suppliers. In the upper level, the aggregator, and in the lower level, the EVs. The aggregator, in the upper level, we model a profit maximizer decisions of the EV fleet operation. In the upper level, the aggregator makes a plan of charging and discharging. It's an individual charging discharging plan. Okay, and in this lower level, try to compute the worst case of availability that reduces the energy which enters into the EV battery. At this variable, the outcome of this variable is the energy which enters into the battery. And in this lower level, the aggregator makes the plan, and this lower level trying to find the worst case of availability that reduces the interaction with the market and minimize the profits. So the outcome of this lower level is the availability profile. Well, this is the mathematical formulation. It's identical to the deterministic formulation, but there are some differences here. Okay. I don't know when the EV is available, so I don't know when the EV consumes energy, but I know that the energy for all the time periods, the energy consumed by the EV must be greater than the expected daily value of EV demand. And the energy which enters into the battery must be greater than the expected daily value of EV demand. This variable is, as I say, obtained from the first lower level and the availability profile from the other lower level. Okay. Here there are the mathematical formulation of each lower level. This lower level, as I say, compute the worst case of availability that minimizes the energy which enters into the battery, and this variable, okay? And this lower level try to compute the worst case of availability that reduce the interaction with the market to minimize the profit, okay? But if we solve the problem, okay, we need to transform the hierarchical problem into a single level equivalent problem. But we have two problems. In each lower level, the availability has binary characters. So each lower level are non-convex, is non-convex, and KKT condition cannot be applied. So we relax the variable to solve this problem, and now the problems are convex and KKT condition can be applied. But Now, the variability can take any value between 0 or 1. And we want a realistic profile because the EV is available or unavailable. If we observe each lower level, the matrix constraint is totally unimodular. And each parameter is integer. So under these conditions, we can guarantee that the optimal solution takes integer values. Now we can transform the hierarchical program into a single level equivalent problem. To do that, we replace this variable by the dual objective function, this lower level by the dual feasibility constraint, and this lower level by the KKT conditions. Okay. To analyze the method, the proposed approach, we have a case study and we analyze the following metrics: the total cost, the total energy bought, the total energy sold, the deviation from the energy balance of the EV batteries. An example of this deviation is if the EV needs to consume 15 kilowatts and the aggregator can only charge 10 kilowatts, the deviation is 5 kilowatts. And the deviation from the minimum value of energy sold if the aggregator makes the plan of selling 200 kilowatts and in the real time can only sell 150 kilowatts, the deviation is 50 kilowatts. So we can observe that the total cost decrease for the deterministic and the stochastic formulation. The reason is they buy more energy and sell more energy than the hierarchical program because the hierarchical program performs a conservative strategy. But, okay, if we observe the deviation, as we know, the aggregator in the hierarchical program try to mix a plan, okay, to fight with the lower levels. Okay, the lowest level, one lower level try to reduce the energy which enters into the EV batteries, and in the other lower level try to reduce the energy, to reduce the interaction with the market. So the hierarchical program makes a conservative plan to solve that issues. So we observe the deviation from energy balance of the EV batteries. This value, this metric increase in the deterministic and stochastic formulation, and the deviation from the minimum value of energy sold increase for the deterministic and stochastic formulation. And that's the reason. The reason is the hierarchical program performed a conservative strategy. And if we observe the power patterns here in this figure, the hierarchical program buy more energy when the electricity price is not the lowest value. Okay, and the idea is buy energy to charge the EV and satisfy the demand of the EVs and sell less energy than the other method, but sell the enough energy to making profit. Okay. In the other hand, the deterministic and stochastic formulation performs an aggressive strategy. Okay, the electricity price is low here. Okay, we buy more energy than the other methods and sell more energy when the electricity price is the highest value. So that's the reason that the deviation are lower in the hierarchical program. Okay, so the EV's aggregator market participation model is simple because we model the uncertainty using a few intuitive parameters. It's effective because the aggregator makes a plan against the adverse situation of the EVs, and efficient because you can scale the program. Okay, we achieve reductions of deviation from energy balance of the EV batteries, but the reduction comes at the expense of increasing the total trading cost. The computational speed of the proposed model is up to 25% faster than the stochastic counterpart in a real size case. Okay. Okay, if you, for more details, you can read the paper, the article that is published in IEEE transactions on smart grid. That's all, and thank you for your attention. If you have any question.